All right, this is what I believe to be the last video about hybridization. Let's look at things that violate the octet rule. So things that have geometries on the right side of the periodic table. Okay, let's look at an example of, let's just try a few examples, and it kind of works the same way we've been doing the previous examples, but I just want to work through a few to make sure you get it. The reason these things violate the octet rule is because they have a d orbital at their disposal. So let's try PCl5. This is a real molecule. If you were going to draw it, we would expect it to form a trigonal bipyramidal geometry. I don't necessarily need you to be able to sketch this, but you know, it would kind of look like that. The chlorines would all have dots on them. Hell, I guess I'll be thorough and draw everything. All right. There's your molecule. Okay. In terms of the phosphorus in the middle, phosphorus has an s orbital and 3 p orbitals, and we would expect it to be neon 3s2 3p3. So we'd expect these to be paired, these to be all unpaired, but we know we have 1, 2, 3, 4, 5 bonds, so we need 5 unpaired electrons. Well, the reason this can violate the octet rule is because there is an empty d orbital. So this is 3s, 3p, and even though we're not using it, this is technically 3d, which means it is available. So we have 1, 2, 3, 4, 5 bonds, so we need 1, 2, 3, 4, 5 unpaired electrons. Okay? We have 5 equivalent bonds. We have 5 things. There's no pi bonds in here. So literally we just merge what we have here, which is a 1, 2, 3, 4, 5 bonds. And it's made of an S, 3 Ps, and a D. So this would be the hybridization of that phosphorus in the middle. A little weird, but it still follows the same logic we were doing before. If you were somebody who's just trying to memorize this and ignored all the details, this is going to be difficult. For anything that doesn't violate the octet rule, you can pretty much just memorize this. For these ones, you have to know the process. Okay, let's try a few more examples here. So let's try SOCl2. Okay, if you go through all the legwork, it essentially looks like this. I'm assuming at this point that you can do Lewis structures and predict geometries using the table. I kind of have to assume that you can do this. So what we have is 1, 2, 3, 4 equivalent groups. We have a sigma bond here, a sigma bond here, a sigma bond here, and even though this isn't a bond, it's kind of like a sigma. Like it's not a pi bond. But we do have 1 pi bond. So the sulfur, which is the central atom, we would expect to have an S, 3 Ps, and 5 d orbitals at its disposal. We have 1, 2, 3, 4 unpaired electrons and 1 set that are paired. So we start with the paired ones, and then we do 1, 2, 3, 4 unpaired. 1, 2, 3, 4. One of these is a pi bond, which has to be made out of a p orbital. Doesn't really matter which one, but we have to pick an unpaired p orbital. And then, just like before, we merge whatever is left. We have an S, 2 Ps, and a D. And it's 1, 2, 3, 4 orbitals. And we also have a p orbital just sitting over here making a pi bond. But what we have is an S, 2 Ps, and a D. So this would be sp2d. I am fully aware there are 2 electrons in the sulfur. We are counting orbitals, not electrons. So we have 1, 2, 3, 4, 5 electrons to shove in here. And what we end up with is this is the lone pair, which we see right there. These are your 3 sigma bonds that are connected to it, which I guess I probably shouldn't label that as sigma. 1, 2, 3 sigma bonds connected to it. And then the p orbital is used to make the pi bond. So it should sync up with your geometry, but the hybridization for this would be S. We're trying to describe what the hybrid orbitals are made of. This would be an sp2d. A little weird, right? Anything that's going to violate the octet rule will have a D or a D2 in it somewhere. Okay, let's try one more example of things that violate the octet rule. Let's try Sf6 Sulfur Hexafluoride. This would be a octahedral geometry if you go through the legwork. Okay, and the sulfur would have 1, 2, 3, 4, 5, 6 things bonded to it. So a sulfur, we would expect it to have an S, 3 Ps, 1, 2, 3, 4, 5 D orbitals available to it. We have 1, 2, 3, 4, 5, 6 electrons in there. 6 bonds. So every time you see a bond, you need an unpaired electron. Every time you see a lone pair, you need to pair them up. We don't have any lone pairs on the sulfur. We also don't have any pi bonds. They're all single bonds. So we just merge what we've got left. We have 1, 2, 3, 4, 5, 6 orbitals. And we have 1, 2, 3, 4, 5, 6 electrons in there. And it is made of an S, 3 Ps, and 2 Ds. So this is the hybridization for this sulfur. Okay, sp3d2. It's a little weird, but it's not like impossible. Okay, let's try just some random examples and kind of show how this works. So let's say we had an organic molecule that has lots of central atoms, and what we're going to look at is what's the hybridization of every central atom. I'm going to draw everything as Lewis structures, so everything's going to be like 90 degrees, and that's okay. All right, so if you're going to do this, what I would do is, if I had this molecule already drawn for you, I would have arrows pointed at each of the central atoms and ask, what is the hybridization? So the first thing I would do is, honestly, I tend to not label all the sigma bonds because they are always going to be there. You almost have to assume they're there, but the pi bonds we do have to account for. So there's no double bonds here, but there is a double bond here, which would be a sigma bond, and then the other one would be a pi bond. Here we have a sigma bond and 2 pi bonds. So I would go ahead and label your pi bonds first. This nitrogen has an S and 3 p orbitals to work with. None of them are being used up as pi bonds, so this should be sp3. Okay. This carbon has 1, 2, 3 sigma bonds. It has an S and 3 p orbitals to work with. One of those is being used as a pi bond, so we have an sp2 as our hybridization. I literally do it on my fingers. Okay, this one has all sigma bonds, so we have an S and 3 Ps to work with, so sp3. Okay, for this carbon, we have an S and 3 Ps to work with, but we have 2 pi bonds. So 2 of these are going to get used, so we have S and a P is all that's left to make hybrid orbitals, and it should work out. Okay, you can also double check this. We have 1, 2, 3, 4 equivalent groups, and we have 4 atomic orbitals making these hybrid orbitals, and S and 3 Ps is 4. Here we have 1, 2, 3 sigma groups, and we have an S and 2 Ps, which is 3 groups. Here we have 1, 2, 3, 4 groups, sp3. That's 4 groups total. Here we have a sigma bond here and a sigma bond here, so there's only 2 groups, so an S and a P would be 2 groups. Okay, it's still consistent, but this is kind of the way to think through it. The reason we care about this, I guess I should point this out, the reason we care about this is if you make it to like organic chemistry, we deal with long organic molecules and carbon chains all the time. And things react differently depending on whether they're sp3 or sp2 or sp. And being able to just spot that really quickly on the fly makes life a whole lot easier when you're deciding how to react to things. Like if you're having to predict the outcome of a reaction, this actually, like, being able to spot this really quickly and work through this kind of makes the process a whole lot easier. So, all right, thank you.